Late August 1944, northern France. The rain had turned the Norman roads to a slick, chalky paste, slowing the American advance to a crawl. The American tank would never fight again. The German crew marked a tally on their gun shield, reported the destruction of the vehicle to their command. The United States Army had to build an invisible, mobile factory system that followed the armor directly into the fire. A few miles behind the fighting in northern Europe, hidden beneath camouflage netting in a scarred farm field, a different kind of army operated. There were no static factory floors here, no poured concrete foundations, and no overhead rail cranes. This was the domain of the United States Army Ordnance Department. To support the modular architecture of the Sherman tank, the military had developed a doctrine known as echeloned maintenance. It was a system designed to push heavy repair capabilities as close to the bleeding edge of the battlefield as possible. The doctrine divided repair work into strict tiers. The first echelon was the tank crew itself. Drivers and mechanics handled daily maintenance, adjusting track tension, cleaning air filters, and replacing minor exterior parts. But when a tank suffered heavy battle damage, a cracked engine block or a blown suspension, the problem passed to the second echelon. This was the battalion maintenance platoon. Stationed just out of direct artillery range, these platoons were heavily motorized. They did not wait for broken tanks to be brought back to them. They went out into the field to get them and fell back to the next defensive line. They had blunted the spearhead, but 2 days later, the German line was hit again. The backbone of this forward recovery was the M32 armored recovery vehicle. The American military recognized that sending unarmored trucks into a firing line to rescue 30-ton machines was a death sentence for the recovery crews. Instead, the M32 was built on a modified Sherman chassis. It was stripped of its main gun turret and fitted with a massive 60,000-pound internal winch and an 18-foot folding A-frame boom crane. Because it was thickly armored and shared the same tracks and engine as the tanks it was rescuing, the M32 could drive directly into contested mud, hook a steel tow cable onto a smoking hull under mortar fire, and drag it back to a secure forward assembly point without waiting for the sector to be fully cleared. If the damage was too severe for a quick field fix by the battalion mechanics, the tank was handed back to the third echelon, the medium maintenance ordnance companies. These units functioned as highly mobile, independent factories located roughly 10 to 15 miles behind the fighting. They operated out of heavy shop trucks loaded with arc welding rigs, power lathes, heavy-duty air compressors, and vast bins of standardized hardware. When the combat units advanced, these ordnance companies did not stay behind in permanent depots. They packed up their heavy canvas blackout tents, and the numbers did not make sense. The defending commanders had read the after-action reports. They had counted the smoking steel husks left on the roads, stowed their tools, and followed the armor. The American repair line was a moving supply chain that adapted to the speed of the tactical advance. This mobile factory system relied on a ruthless standardization of parts. The maintenance companies did not forge steel plates or manufacture gears in the mud. They were supplied with pre-assembled modules. Transmissions, engines, and suspension bogies arrived in wooden crates directly from the ports. A mechanic in the field did not need to know how to rebuild a shattered differential from scratch. He only needed to know how to unbolt the broken housing and drop the crated replacement into the hull. This allowed the ordnance companies to process damaged armor with industrial speed. On paper, the doctrine was a triumph of logistical engineering. It perfectly matched the modular design of the Sherman tank, theoretically guaranteeing that a shattered formation could be rebuilt within days. But doctrine written in Washington rarely survives first contact with a real war completely intact. The true test of this echelon system would not be found in a training manual. It would be proven in the freezing rain, working by the light of shaded flashlights, as mechanics tried to piece together a crippled tank before the next dawn offensive. Midnight in the Normandy bocage, the rain had not stopped, and the mud was deep enough to swallow a man's boots. They knew exactly how many American tanks they had crippled in the sector. By every law of attrition, the opposing American armored battalion, a mile behind the front line, an M32 armored recovery vehicle reversed slowly toward the dark shape of a disabled Sherman. This was the same tank the German anti-tank crew had shattered days earlier. Under the strict blackout conditions, there were no floodlights. The recovery crew worked by touch and the faint red glow of hooded flashlights. They waded into the freezing mud, dragging thick steel cables from the M32's internal winch. They hooked the heavy steel eyes onto the Sherman's towing points. The recovery vehicle's engine roared. The winch took the immense strain, and with a heavy sucking sound, the 30-ton casualty was dragged free from the ditch. It was towed miles rearward to an ordnance maintenance company hidden in a farmyard. Here, beneath a massive canvas blackout tent that hid the bright sparks of arc welders from enemy aircraft, the theoretical doctrine became physical labor. The air inside smelled of ozone, raw diesel, and the sharp metallic tang of burnt gear oil. The mechanics waiting for the tank did not have time for careful diagnostics. The armored battalion was scheduled to resume its attack at dawn. The M32 pivoted, extending its 18-foot A-frame boom crane directly over the nose of the crippled Sherman. Men in grease-soaked coveralls climbed onto the sloped armor. Should have been combat ineffective, bled down to a fraction of its original strength. Instead, the American formation rolling over the ridge was at near full capacity, holding heavy breaker bars. They attacked the row of massive bolts, securing the damaged front differential housing. They did not gently dismantle the fighting compartment. They unbolted the armor itself. When the bolts were cracked and removed, the crane took the weight. With a heavy groan of shifting metal, the entire shattered transmission assembly was pulled free, leaving a gaping cavity in the front of the tank. The ruined machinery was lowered into the dirt and pushed aside. Nearby, crowbars tore open a heavy wooden crate. Inside sat a pristine, fully assembled transmission and final drive, thick with protective grease. The M32's crane hooked the fresh module, lifted it into the air, and swung it over the open hull. The mechanics guided the massive steel unit into the cavity. It slid into place. The heavy bolts were driven back in and torqued down tight. The interior drive shafts were reconnected. Outside the hull, men hammered heavy steel pins to relink the track over the fresh drive sprocket. They poured gallons of fresh oil into the new housing. The driver climbed into his seat and hit the starter. The engine caught, sending a cloud of exhaust into the damp air, and the tracks churned the mud. By the time the pale morning light broke over the fields, the defenders faced an impossible contradiction. They were successfully destroying the metal, but they were somehow failing to destroy the unit. The Sherman was fully combat capable. The vehicle that the opposing force had confidently recorded as a permanent loss was already moving back up the road to rejoin its platoon. This was the midnight resurrection. It was exhausting, freezing labor, performed by men whose hands were permanently stained with grease and bruised by slipping wrenches. But it worked. The modular design had allowed them to bypass the factory entirely. Yet, a single repaired tank is just a local tactical victory. The true terror for the German High Command was not found in one blackout tent. To understand why their defensive lines ultimately collapsed, we must look at what happened when this exact mechanical ritual was multiplied across an entire theater of war. By late 1944, The battle for Europe had become a brutal war of accounting, and the ledgers heavily favored the United States. To understand how the Midnight Resurrections won the campaign, we must scale the work of one muddy blackout tent up to the size of an entire armored division. When a German panzer commander reviewed his daily readiness reports, the numbers were grim. A heavy panzer battalion might begin an offensive with 45 Panthers. After a week of intense combat, the commander might lose 10 to direct enemy fire, but another 20 would likely be paralyzed by mechanical failures. To a German officer trying to hold a crumbling front, there was only one logical explanation. The industrial might of the United States was simply overwhelming: shattered transmissions or broken suspensions. Because of the centralized repair doctrine and the extreme weight of the vehicles, those 20 damaged panzers had to be dragged to railheads and shipped back to specialized depots. For the next month of the campaign, that battalion would be forced to fight with just 15 tanks. The metal still existed, but operationally, the unit was broken. The German commanders naturally applied this same attrition math to their enemy. When they inflicted 50 mobility kills on an American armored division over a 3-day battle, they confidently assumed that division would be stalled for weeks, waiting for replacement tanks to ship across the Atlantic Ocean. Instead, the American readiness reports told a story that completely defied German logic. An American armored division might take catastrophic hits on Monday, leaving dozens of Shermans disabled in the fields. But by Thursday, the division's operational readiness rate would often hold steady at 80 or 90%. This was not because 50 brand new tanks had rolled off a cargo ship that morning. It was because the forward ordnance companies were operating as a massive, continuous recycling loop. The Sherman hulls were treated as reusable platforms. If a tank was knocked out, the broken module was unbolted, a fresh subassembly was dropped in, and the machine was sent back to the line. A single Sherman chassis might suffer 3 separate mobility kills in a month. Detroit and Chrysler must be flooding the ports of Europe with an endless, continuous river of brand new tanks, replacing every single loss. It might take a blown suspension one week, a cracked differential the next, and a destroyed engine the week after that. Yet, because of the echeloned maintenance system, that same tank could be back on the firing line the morning after each engagement. The Americans were not just relying on new manufacturing, they were resurrecting the exact same metal over and over again. This was the ultimate attrition equation. The German military built bespoke machines for the perfect engagement, hoping to win the war one individual tank duel at a time. The American military built a logistical system to sustain a relentless operational tempo, knowing that campaigns are won by whichever army can field the most combat-capable formations on day 30 of an offensive. The Sherman did not need to win every single duel. It just needed to return to the front faster than the enemy could replace its own losses. The German High Command was not blind to this reality. By the winter of 1944, their intelligence officers and frontline commanders realized they were fighting an enemy with an impossible recovery rate. They could clearly see the results of the modular design and the forward maintenance echelons. The blueprint of American armored dominance was laid bare in every captured Sherman and every overrun repair depot, with a fresh machine shipped directly from the factory line to the front. It became a comforting myth for a defeated army, the idea that they were, but recognizing a superior system is not the same as implementing it. If the American philosophy of repairability was clearly winning the war of attrition, why did the German military refuse to simply copy it? To understand that failure, we have to look at the severe cost of their own complexity. When a German frontline commander recognized the brilliance of the American repair cycle, he was powerless to replicate it. The German military could not simply decide to adopt modular maintenance in the autumn of 944. Their entire industrial and doctrinal foundation was already locked into a rigid, inescapable trap of their own design. The cost of their engineering complexity had become fatal. To understand why the German war machine was paralyzed by its own ambition, look at the physical labor required to perform basic maintenance on a Panther tank. If an American Sherman hit a landmine and shattered its suspension, mechanics unbolted the ruined bogie and bolted on a new one. But if a Panther hit that same mine and damaged a single inner road wheel, the repair process was a mechanical nightmare. The German heavy tanks utilized an interleaved suspension system to distribute their massive weight. The steel wheels overlapped each other in multiple staggered rows by limitless mass, drowning under a tidal wave of fresh steel. But the shipping manifests and logistical realities of 1944 tell a different story. To reach one damaged inner tire, mechanics in the field had to meticulously unbolt and remove up to half a dozen heavy outer wheels first. The tank had to be precisely jacked up. The tracks had to be completely broken and pulled away. What took an American ordnance crew an hour to fix with a hoist took a German crew an entire day of exhausting labor, requiring stable ground and specialized lifting gear that was rarely available under fire. The internal architecture was even more punishing. The Panther's transmission was located in the front hull, just like the Sherman. But unlike the American tank, the German design did not feature a bolted, removable front armor plate. The armor was heavily welded and sloped to maximize defensive protection. This meant that when the transmission inevitably failed under the strain of the tank's extreme weight, mechanics could not pull it out the front. They had to go in from the top. To replace a Panther's transmission, a specialized repair crew had to construct a massive, portable gantry crane over the tank. They had to unbolt the 15-ton turret, lift it entirely off the hull, and set it on the ground. Only then could they reach down into the dark cavity of the chassis to extract the broken drivetrain. In the tree line overlooking a narrow intersection, a German Pak-40 anti-tank crew waited in the damp cold. They knew their business. The American supply lines stretching from the invasion beaches were strained to the breaking point. There was no magical conveyor belt delivering a new Sherman. This level of bespoke engineering meant the German military could never build a forward echelon maintenance system like the Americans. They could not fix their heavy armor in a muddy field under a blackout tent. They were forced to rely on centralized rail depots, pulling damaged tanks far away from the front line for weeks at a time. And the heavier the tanks became, the harder they were to move. When a 60-ton Tiger tank broke down, it required 3 heavy recovery half-tracks just to tow it. If those recovery vehicles were not instantly available during a retreat, the crew had only one option. They had to plant demolition charges inside their own masterpiece and abandon it. The German industrial base could not pivot. Halting production in 1944 to redesign their tanks for modularity would have meant shutting down the factories for months. A delay they could not afford while fighting a desperate defensive war on 2 fronts. They were forced to double down on complexity, building fewer, heavier machines, hoping that raw combat power could offset their logistical paralysis. The defenders on the Norman roads had originally believed that armored warfare was decided by the thickness of the steel and the velocity of the gun, to the front line within 48 hours of a loss. The tanks rolling over the ridge were not all factory-fresh replacements, but as they watched the phantom formations of recycled Shermans roll relentlessly over their positions, the true nature of the campaign was finally revealed. Late August 1944. The German Pak-40 crew retreating down the muddy Norman road left behind a smoking Sherman with a shattered front transmission. They carried with them a profound, fatal misunderstanding of the enemy they were fighting. Through their Zeiss optics, They had witnessed a catastrophic mobility kill. By the rigid, heavy engineering standards of their own army, they had permanently removed an armored asset from the campaign. They marked their tally and believed they were winning the war of attrition. But the question of victory in the European theater was never really about which tank had the thickest frontal plate or the highest velocity gun. It was not a contest of bespoke engineering or individual mechanical superiority. It was about operational endurance. It was about the ability to absorb damage and return to the fight faster than the enemy could replace their own losses. The German military built mechanical fortresses that demanded perfection and shattered when they failed. The American military built a modular tool designed to be broken, dismantled, and rebuilt in the mud. Yet, an externally accessible differential housing or a removable engine deck is not a weapon by itself. Modularity is only a theory until human hands put it to use under the friction of war. The phantom formations, that many of them were the exact same vehicles the Germans had confidently left for dead days earlier. The phantom formations that kept breaking the German lines constantly broke. The German defensive lines were not summoned by a limitless supply of factory replacements. They were built, night after night, by the men of the echeloned maintenance system. The true weight of the American armored advantage was carried by the mechanics in the medium maintenance ordnance companies. It was carried by the drivers of the M32 armored recovery vehicles, who often operated with their hatches open, driving directly into contested territory to hook heavy steel cables to smoldering hulls. It was carried by the welders, the fitters, and the supply clerks managing the endless flow of wooden crates from the coastal ports. These men fought a relentless, parallel war in the blackout tents, working entirely by touch and the faint red glow of hooded flashlights. They fought the freezing rain, the deep mud, and the sheer physical exhaustion of wrestling multi-ton engine, blocks, and heavy steel bogies into empty cavities while artillery pounded the horizon. Their hands were permanently stained with diesel, their knuckles bruised from slipping breaker bars, their uniforms soaked in heavy gear oil. They were the invisible architecture of the armored spearhead. By treating the Sherman tank not as a precious masterpiece, but as a heavily armored chassis designed to carry replaceable modules, they completely shattered the German mathematics of war. They ensured that a catastrophic hit on the battlefield was no longer a fatal blow to the division. Were not a product of endless manufacturing, they were the product of a localized resurrection. The opposing force was seeing the consequence. When the sun rose and the American armored columns rolled back over the ridge, the defending German gunners saw an impossible wave of steel. They saw the consequences of an industrial machine they could neither match nor understand. But what was truly advancing toward them was the exhausting labor of the night before. Long after the front line moved forward, the true secret of the campaign remained hidden. Miles to the rear, a scarred farmyard, a pile of twisted, unbolted steel left quietly in the dirt, and an empty wooden crate slowly filling with the morning rain. But they were entirely blind to the machinery operating just out of sight. To understand why a shattered transmission was a fatal blow to a German Panzer, but a temporary inconvenience to an American Sherman, we first need to look at the rigid rules of war the defenders believed they were fighting under. To a Panzer crew in 1944, a tank was not merely a vehicle, it was a heavy, finely tuned piece of engineering. When the PaK-40 gunner in Normandy watched the Sherman's transmission housing shatter, his assumption of a permanent kill was not arrogance. It was a projection of his own army's limitations. In the German mechanized forces, a catastrophic hit to the drivetrain or engine was often a logistical death sentence. The German military built machines that performed brilliantly when pristine, but they were incredibly punishing to repair under the friction of a long campaign. When the lead M4 Sherman of an American armored column lumbered into their sights, they did not aim for the thickest armor on the turret. Consider the Panther tank. It was a marvel of lethal geometry, boasting thick, sloped armor and a devastating high-velocity gun. But its internal architecture was a mechanic's nightmare. If an anti-tank shell cracked a Panther's transmission, fixing it was not a frontline job. The transmission was buried deep inside the armored hull. To replace it, a specialized repair crew had to use heavy gantry cranes to physically lift the entire turret off the chassis. This was not a task that could be performed in a muddy ditch under artillery fire. It required stable ground, heavy lifting equipment, and daylight. The suspension system was equally demanding. The Panther and the Tiger utilized overlapping, interleaved road wheels to distribute their massive weight and provide a smooth ride for the gunner. If a mine or a shell damaged a single inner wheel or fractured a torsion bar, a mechanic could not simply pull it off. They had to unbolt and remove up to 5 heavy outer steel wheels just to access the broken component. When a German tank suffered a mobility kill, the physical act of moving it was a desperate operation. A disabled 45-ton Panther often required 2 or 3 heavy half-tracks or a dedicated Berger Panther recovery vehicle just to drag it out of the mud. They aimed low. At 400 meters, the 7.5mm shell struck the Sherman's lower front hull. The impact was deafening. If the tracks were locked, dragging the tank would severely damage the final drives. Because of this massive weight and complex engineering, the German military relied on a centralized maintenance doctrine. A heavily damaged Panzer had to be dragged to a railhead, loaded onto a specialized flat car, and shipped back to a regional depot, or sometimes all the way back to a factory in the homeland. The machine was eventually salvaged, but for the duration of the current campaign, that asset was completely removed from the tactical board. This was the rigid framework of attrition the defenders relied upon. They measured success by the number of broken hulls left in the fields. When they broke the track and shattered the differential of an American Sherman, they automatically applied their own logistical burdens to the enemy. They calculated the heavy lift cranes, the days of labor, and the specialized rail journeys that would be required to return that enemy machine to the fight. By their logic, a shattered hull was a permanent deduction from the American order of battle. But the American military did not fight by German rules. The Sherman was not built as a bespoke, tightly packed masterpiece of engineering. It was built as a rugged, adaptable tool, shaped by constraints the enemy command never had to consider. While the German gunners marked their kills and retreated to the next hedgerow, sparks showered over the muddy road. The tank jerked violently to a halt, a heavy column of white smoke immediately pouring from its engine deck. They assumed the broken American machines would simply sit and rust. They could not see the hidden logistical infrastructure moving up the road, behind the front line, ready to exploit a design philosophy that favored rapid repair over heavy perfection. Long before the first American tank touched the sand of North Africa or the mud of Normandy, its fate was decided on drafting tables, in Washington and at the Aberdeen Proving Ground. In 1941, the United States Ordnance Department faced a massive geographic problem that the German High Command never had to consider. Germany built tanks to roll directly out of a factory onto a reinforced rail car and into combat on the same continent. The American military had to project armored power across an ocean. Every tank the United States produced had to fit into the cargo hold of a Liberty ship. It had to be lifted by standard commercial dockside cranes, which strictly capped its weight at just over 30 tons. It had to cross thousands of miles of submarine-infested water, be unloaded at hastily secured often severely damaged ports, and then fight its way across foreign soil. Because of this massive logistical tether, the Ordnance Department knew they could not rely on sending damaged vehicles back to a central hub for heavy repairs. Through their Zeiss optics, the German crew watched the tracks unspool into the dirt. The drive sprocket was shattered. There was no railway linking the front lines in Europe back to the assembly lines in Detroit. The repair facility had to come to the tank. Therefore, the design of the medium tank M4, the Sherman, was driven by a ruthless, unglamorous mandate. It was not built to be an impenetrable, heavily armored fortress. It was built to be a reliable, highly accessible platform. The engineers designed the tank around the concept of the subassembly. Instead of a continuous, bespoke hull that sealed the mechanical components away from mechanics, the Sherman was built to be taken apart in the field. The Ordnance Department demanded that major mechanical systems be easily accessible from the outside. If an engine failed or was destroyed, the military did not want mechanics wasting days carefully dismantling the fighting compartment to reach it. They demanded a system where a handful of men with a standard hoist could unbolt the rear deck, pull the dead engine out, and drop a fresh power plant into the hull in a matter of hours. The German military viewed their heavy tanks as complete, singular weapons, prioritizing maximum combat capability in a single engagement. The American military viewed the tank as a collection of easily replaceable parts bolted together, prioritizing the ability to sustain an offensive over months. This philosophy meant that raw armor thickness or sloped defensive geometry was sometimes compromised to allow for large access panels, removable plates, and exterior bolts. The front transmission housing was cracked wide open. Seconds later, the American crew scrambled out of the hatches and retreated into the ditches. To a tank crew facing high-velocity enemy guns, this structural compromise could be a terrifying reality. But to the architects of the American war machine, it was a necessary trade-off to ensure that a damaged vehicle was never permanently lost to the campaign. The blueprint was set. The Sherman was a machine optimized for global shipping and modular replacement, constrained by the weight limits of dockside cranes and the dimensions of cargo hatches. It was an industrial solution to a logistical problem. But a blueprint is only a theory until it takes fire. How did a requirement meant to satisfy maritime shipping translate into a decisive tactical advantage on the ground, where the metal met the mud? Look at the nose of an M4 Sherman. The steeply sloped front hull ends in a massive, rounded steel casting that houses the transmission, differential, and final drives. To a casual observer, it looks like a solid wall of armor, but a mechanic looking at the same piece of steel sees something entirely different. They see the bolts. Instead of sealing the transmission deep beneath the turret ring, the Sherman's engineers placed it at the very front of the vehicle, protected by a heavy armored cover that was bolted, not permanently welded, to the main hull. If an anti-tank shell cracked the differential exactly like the mobility kill the German crew scored in Normandy, for the German gunner, the math of the battlefield was simple and final. The enemy tank was not entirely vaporized, but it did not need to be. The repair did not require a heavy gantry crane to dismantle the fighting compartment. A recovery crew could simply unbolt the damaged front cover, attach a hoist, and pull the entire shattered transmission assembly straight out of the nose of the tank. They could then slide a fresh, pre-assembled unit into the cavity, tighten the heavy exterior bolts, and reconnect the drive shaft. This same modular architecture governed the rear of the vehicle. The engine compartment was enclosed by large, heavily hinged doors and bolted armor plates. The Sherman was powered by several different engine types during the war, from aircraft-style radials to massive V8s, but they all adhered to the same spatial rules. The fuel lines, electrical harnesses, and cooling systems were designed for rapid disconnection, If an engine caught fire or threw a rod, mechanics did not have to operate in a cramped, dark steel cave. They unbolted the rear deck, connected a standard boom crane to the engine lifting rings, and pulled the dead power plant straight up and out into the daylight. A new engine could be dropped into the empty bay and connected in a matter of hours. But the most common battlefield casualty was the suspension. Landmines, high-explosive artillery, and anti-tank fire routinely shredded tracks and blew road wheels into twisted scrap. Here, the Sherman's design was drastically different from the heavy German armor. Instead of a complex web of overlapping wheels and internal torsion bars, the Sherman utilized the volute spring suspension system. It was paralyzed. Its drivetrain was severely compromised. In the brutal accounting of armored warfare, a catastrophic mobility kill was a permanent kill. The road wheels, springs, and return rollers were grouped together into self-contained external units called bogies. These bogies were bolted directly to the flat vertical side of the lower hull. If a mine destroyed a wheel or shattered a spring, a mechanic did not have to dismantle a layered puzzle of heavy steel discs. They simply brought up heavy tools, unbolted the entire ruined bogie unit, and let the twisted metal fall away into the dirt. Then, they lifted a brand new, completely assembled bogie unit into place, bolted it to the hull, and strung a new track over the wheels. The vehicle was essentially a massive, lethal construction set. The metal was designed to be modular, exposed, and entirely replaceable. The armor was thick enough to stop most glancing blows. But the true defense mechanism of the Sherman was its physical anatomy. It was built to absorb catastrophic mechanical damage and shed its broken parts in the field. Yet, a modular design is useless in a vacuum. A shattered transmission cannot unbolt itself. A multi-ton engine block requires heavy lifting gear, and a new suspension bogie must be transported from a supply dump to a muddy ditch on the front line. The physical architecture of the tank was only the visible half of the equation. To make this rapid cycle of repair a reality,